this lesson is an overview of Unit 5. It's all about equations. It's about balancing equations. It's about determining physical states. It's about determining the products of equations. It's about classifying equations. It's about complete and net ionic equations. So you have to be able to balance combustion reactions, predict the products, figure out the physical states, and then you're going to balance the equation. And we're going to use atom inventories every time. If you don't have an atom inventory, that's a lot of points you lose. So make sure you always include an atom inventory. Some of these equations are fairly easy to balance, but I require an atom inventory just to show. So 3 carbons, 8 hydrogens, 2 oxygens to start. Over on the other side, it's always 1, 2, 3. To balance the number of carbons, we're going to put a 3 here. That's going to change the number of carbons and oxygens. So now we have 3 carbons, and adding up the oxygens, and I'm showing you this almost every time we do a combustion reaction, that you add up on the side. I've seen so many students do the math wrong for figuring out the number of oxygens, and it's mostly, I think, because they don't take the time to actually put it down on paper. Then they go and turn in their test 20 minutes before the period's over, and they've done the math wrong. They didn't even bother checking the math. Please don't do that, okay? Be more cautious and careful. Do the math on paper and make sure you've got it right. So there's 3 times 2, that's 6, plus the 1 here. So right now, we have 7 oxygens. It seems so simple. That math seems so simple, but sometimes it just kind of gets away from you. If you put it down on paper, it's easier to see that you make mistakes. All right, so we have 8 hydrogens on the left and only 2 on the right. To get 8 on the right, we're going to put a 4 here. That's going to change because there's hydrogen and oxygen in that formula. The number of hydrogens and the number of oxygens. The number of hydrogens is now 8, and the number of oxygens, 3 times 2 is 6, plus 4 times 1 is 4, so that's 10. So we've got 10 oxygens here. To get 10 oxygens on the left, since I have a subscript 2, I'm going to put a 5 here. That's going to change the number of oxygens over here to 10, and this is balanced now. Okay? All right, then, let's do this. I want you to write it down just the way I'm going to put it down on paper, okay? Okay. And then I want you to put a box in here like this. And in this box, I want you to make sure that you write a complete ionic equation here. Complete ionic equation, if there is one. And then write another box under that for your net ionic equation. Now, just so you know, every once in a while, the complete ionic equation and the net ionic equation will be the same. Because when you split things up into ions, you find out that there's nothing that can be canceled. Okay, nothing you take out. So just so you know, sometimes they're the same. All right, and then I want you to show me your work for balancing the equation down here like this. Okay.
I want to be the other way around. I balance it first and then do the...
Right, but I want to see the balancing down here. So I want to see the balanced equation up here, but I want to see your work down here. So your atom inventory is going to go down here, okay? So what I'm going to do is show you in red what will be required for a problem like this. Everything that I'm going to write down now is going to be required. So you need to figure out the physical state of this. Well, if you look on your solubility rules, you'll see that chlorides are always soluble, while there are some exceptions. Hydrogen is not. Further, this is a strong acid, and strong acids are always soluble. So this is going to be aqueous. I should have said there was water around. I didn't say that. If water present. So I think didn't I assign a couple of homeworks on this? Well, I said water was present. Okay. And so we're going to look and see if this is going to be soluble or not. All right. And I'm going to look in here and I see that ammonium is right here. Okay. So this is the ammonium ion. If you didn't know that was the ammonium ion, well, there's another place to look in the test references here. And anytime you have more than two elements in a formula, you're going to look on the common ions list and see if you can find a polyatomic ion. Well, there's two polyatomic ions here. There's ammonium. It's right down here. That's this first part. And you kind of know that first part is a polyatomic ion because it's inside of parentheses. The only thing you use parentheses for is to show that you have more than one polyatomic ion. I mean, more than one atom bonded together into a polyatomic ion. Okay? So if it's inside of parentheses, it's almost got to be a polyatomic ion. There are some exceptions to that, but we haven't covered any of those. They're not going to come up in this class. Then you're going to look here and you're going to see, well, we got this plus two more things, so maybe that's a polyatomic ion. You're going to look around and find carbonate right here. And since we used that quite a bit because I explained how you can form gases and things from carbonates, you should recognize that. We've used it enough. Okay, you just got to kind of know that CO3 is a carbonate. All right, and you can look it up and find the charge and that sort of stuff to be sure. But it says that ammonium ions on the solubility rules, those compounds with ammonium ions are always soluble, and there's no exceptions over here. So this is going to be aqueous. All right, so now we're going to put the front part of this with the back part of this. The reason I want to do that is I have an acid. That's a two-part compound. I have polyatomic ions here, so that's an ionic compound. So whenever you've got an acid or ionic compounds, you're going to create, if you have both of these are going to be acids or ionic compounds, then you're going to have a double replacement reaction. If there's any reaction at all, it's going to be double replacement. Yeah, it is on the list. So carbonate is on the list. Let's see, it's right down here. It says carbonates are insoluble except when they're bonded with group 1 and ammonium. So, you've got to look at the exceptions. That's really critical. All right? Okay. So hydrogen's going to go with the CO3, the carbonate. And ammonium is going to go with the Cl, the chloride. So now the subscripts only travel if they're part of a polyatomic ion. So this subscript traveled to here because that's part of the polyatomic ion carbonate. This 4 subscript traveled over here because it's part of the polyatomic ion ammonium. But this subscript 2 here did not travel. It's not part of a polyatomic ion. It's counting the number of polyatomic ions, but it's not part of the polyatomic ion. Now we need to balance the formulas. Hydrogen ions have a 1+ charge. Carbonates have a 2 negative. Now you can look that up on the common ions list. We just looked at it a minute ago. That's 2 negative. So I need 2 hydrogens to balance out this carbonate. Okay? Because that's 2 negative. Well, that should send up red flags and sirens and wheels and bells, whistles and bells. I can't even talk today. Whistles and bells in your head because that is something that's inherently unstable. Now, when you make this stuff, it automatically decomposes. So we need to rewrite the equation then to show what it decomposes into. So I'm going to stop with this part and rewrite the equation down here. You can balance the equation up here, but if anything else you're going to put down here, okay? So let's put this down here in this way. HCl and NH4, CO3, aqueous. And now I'm going to write out what this decomposes into. And you just got to know this. All right? It's something you got to memorize. It's something you got to be able to use. Now, this automatically decomposes into water and carbon dioxide. And water is going to be a liquid. Water is a gas if there's lots of heat, but there's nothing here that would tell you there's heat. In the previous equation with combustion, this is a gas because combustion always creates heat. Okay? And so we've got water down here, and we've got CO2, and CO2 is always a gas. And then we've got the other part of what's left, which we haven't balanced yet. I haven't finished balancing that yet. And we haven't figured out its physical state either. Okay? So don't assume that this is a combustion reaction because it got water and CO2. This water and CO2 is not the result of combustion. Combustion requires a fuel and oxygen. Okay? And in this class, all our fuels are going to be hydrocarbon fuels. Okay? So this is not combustion. This, becoming this, is decomposition. Okay? These two things here, becoming these two things, is double replacement. So this equation here is both double replacement and decomposition. Yeah, you could balance this out and then split it up. Okay, if you wanted to, that's fine. But I like to do it this way first. Okay, because it really comes out to be the same. All right. So it says that ammonium and chlorides. Well, ammoniums are always soluble. Chlorides are soluble with some exceptions, but ammonium is not one of those exceptions. So this is going to be aqueous. All right. So we formed water and we formed CO2, and both of those are driving forces. If I just stop right here and look at those, I would say this is aqueous and that's aqueous. There's no driving force. I'd write NR and stop and go home and lose all the points for all this other stuff. Okay? So don't forget, when you get this, you've got to write the decomposition because there's your driving force. If you have this compound, you just got to know. Just something you got to know. It's like you know what directions to drive to go to school, or what clothes to put on in the morning before you walk out of the house, or how to turn on the lights in your room. You just got to know it. Okay? Just stuff you got to know. All right. Now we can balance the equation, and so we're going to write down all the elements we have in on the left-hand side, on one side of our atom inventory, and all the elements on the other side of the atom inventory should have the same elements. We're going to count them all on two different sides. So here's the H, here's the Cl, here's the nitrogen, here's the carbon, and here's the oxygen. And I want to make a kind of grid here to keep up with everything. This is an inventory. Just like you take an inventory in a store, you got to keep up with everything. You got to have a list of all the stuff in the store. That's what this is right here. And you got to count them all. Okay? And in this case, we're going to count them in two different places. So over here, I've got one hydrogen here, plus over here, I've got 8 hydrogens. Okay? So right now, I've got 9 hydrogens. I've got 1 chlorine. Let's see, I've got 2 nitrogens. This parentheses with the 2 outside, that 2 right there means there's 2 of everything inside. So if each ammonium has 1 nitrogen, but I've got 2 ammoniums, then I've got 2 nitrogens. Okay, I've got 1 carbon and 3 oxygens. Okay, I'm going to go to the other side of the equation now and count everything. And right now I've got 2 hydrogens here plus 4 over here. So right now I've got 6 hydrogens. Okay? I've got 1 chlorine. I have 1 nitrogen. I've got 1 carbon. Oxygens, I've got 1 here and 2 here, so I've got 3 oxygens. So I've got to get everything balanced, and I can look and see that I've got an imbalance in the number of nitrogens and an imbalance in the number of hydrogens, and you're always going to save oxygen for last. It's already balanced. Hydrogen for next to last. It's unbalanced. And nitrogen. So I'm going to start with nitrogen because you're supposed to leave oxygen to balance last and hydrogen for next to last. So the only thing left to balance right now, in the beginning anyway, is for nitrogen. Okay? So I'm going to put a 2 over here in front of the species containing nitrogen and recount nitrogen, hydrogen, chlorine over here. Now by putting a 2 here, that means I have 2 hydrogens here plus 2 times 4 are 8 hydrogens over here, so that's 10 hydrogens. That makes sense? All right. So that's going to change the number of hydrogens. Actually, I'm going to mark out hydrogen, nitrogen, and chlorine because I'm going to be changing all of those. So now I have 10 hydrogens. Let's see here. I've got 2 nitrogens now. I've got 2 chlorines now. Okay. Now I want to go back over to the other side and balance the chlorines. Remember, I'm saving hydrogen for last. So I've got 2 chlorines on the right. I've got only 1 on the left, so I need to put a 2 in front of the species containing the chlorine. Okay, and that's going to change the hydrogens. I'm sorry, hydrogens here and chlorines. I shouldn't have marked that out. That means now I have in the hydrogens, I've got 2 hydrogens right here, and plus the 8 hydrogens here. So I've got 10 hydrogens. Okay, I've also got 2 chlorines, and everything's balanced. Just got to be careful and take it step by step. Okay, the math isn't hard. Balancing equations don't make it hard. It shouldn't hard. Don't make it hard. There are some that are more difficult, but only because of the amount of math. But this math is addition and simple addition and multiplication. Not even high-level multiplication. Not even high-level addition. Simple, straightforward. Grade school, elementary school, multiplication and addition. Okay, it's just a matter of keeping up with it. So don't forget to write it down here when you're doing the math to make sure you keep up with it, so you can keep up with what you're doing. Because there's a lot of it, but it's little simple stuff you got to do. All right. So now we're going to go back up here and write our complete ionic equation. So we're going to split up this because this is an aqueous acid. So we're going to have 2 hydrogen ions that are aqueous. So this is just like when we first wrote these balance formulas. We're just undoing that process. Hydrogens have a 1+ charge and chlorines have a 1- charge. And there are 2 chlorines because of this 2 outside. 2 chlorides, really, because once it's a negative ion, monoatomic ion, you have an IDE ending. All right, this is aqueous, and it's made of 2 polyatomic ions. You keep the top polyatomic ions together. Polyatomic ions tend to stay together. I've got 2 ammoniums. If you go back and look at your your common ions list, if you didn't know this already, we've used ammonium a lot. I hope you would know it. But if you don't, you can look at here and see that it's got a 1+ charge. And since this compound is aqueous, these ions are aqueous. And then we got a carbonate. And this is an aqueous compound, so this carbonate is going to be aqueous. There's only 1 carbonate. It has a 2- charge. If you didn't know that, you'd look right here and find it. Okay, it's one of your test references. You always have that. Always have access to it in this class. Okay, and so that's everything on the left-hand side. Go to the right-hand side. This is not aqueous, so it's not going to split up. So water is not aqueous. Okay, it's not an ionic compound. It's not an acid. And if you're going to split it up, it has to be acid or ionic, and it also has to be aqueous. Okay, if it doesn't meet both those conditions, acid or ionic is one condition, aqueous is the other condition. If it doesn't meet both those conditions, you don't split it up. Okay, and so this doesn't split up. It's neither ionic or acid, and it's not aqueous. Now, technically, there are conditions where water behaves like an acid, but in this case, it's not an acid. Okay, so we're just going to leave it just like it is, H2O, liquid. And CO2 is not an acid, and it's not ionic, so it's not going to split up, and it's not aqueous either. And so this is aqueous, and it's ionic, so we're going to split it up. Now, this 2 outside means I have 2 of this polyatomic ion and this monoatomic ion. So we've got to have 2 of those when we write it up here. 2 NH4 plus aqueous. Chlorine, I got 2 of those, 2 chlorides, aqueous. Okay? And that's a complete ionic equation. Then, to write a net ionic equation, I just get rid of anything that's exactly the same on both sides. Okay? Remember that if you use the sports analogy, the things that are doing something are in the game, and the things that aren't doing anything are on the bench. They're the spectators. And so these ions, like these 2 chlorides here, they're not changing. They're exactly the same on both sides. So they don't change. Now, I know somebody's going to get this wrong when they see this, okay? There's somebody that's going to look at this, and they're going to say, well, here's a hydrogen, and here's a hydrogen. That's the same. They're not the same. This is a hydrogen ion. It's aqueous. This hydrogen is bound up with this oxygen to make a water molecule that's not aqueous. It doesn't split up. It's not an ion. So these 2 are not the same. The chlorides are the same. The ammoniums are the same. Those are the spectators. They didn't change. They're on the bench. They're not in the game. We're going to leave them out of our net ionic equation. Okay? What we're going to do is write only those things that do change, okay? So this hydrogen ion changes, this carbonate changes, and we've got H2O and CO2 on the right-hand side. Oh, I wrote the wrong thing. That's not going to be there. It's supposed to be the CO3 that's going to be there, not the Cl. Alrighty, let's make sure we get rid of that. I'll come back and finish that after that has a chance to dry. On the other side, we're going to have H2O and CO2. Alright, so we've got CO3, 2 negative, aqueous here. Okay? And that's the net ionic equation. So there shouldn't be a coefficient 2 here in the front of this. Okay? Because there isn't one up here. I just left it there a moment ago when I was making that change, because I started to write down the wrong thing. Alright? So, my mistake actually is a good lesson for you guys. You know, everybody makes mistakes. That's why you want to go back and double check your work. Alright? Kind of take a deep breath, maybe even come back to it. When you finish your test, if you've got 15 or 20 minutes left, go back and look at your work and make sure you've done all the little pieces right. Okay? So these two problems I've highlighted here on the video from yesterday, those are the problems I asked you guys to do for homework. And the first one on here, number 32, is a single replacement reaction. Okay?
We need to switch.
Yeah, you need to switch with somebody else who also has their homework. Unless you want me to grade it. I mean, I can grade your paper. I'll be glad to. I do that for some students every day. It's fine with me. It just gives you immediate feedback, especially since we have a test tomorrow. It's kind of nice to have immediate feedback. All right, so this is the first question that was asked of you. It said it's in water. I didn't write that down, but it says that this is in water. Okay, has everybody exchanged their paper?
Yeah.
Okay, so if it's in water, then we need to look at this compound and see if it's going to be aqueous. Now this one right here, this is a metal. If you didn't know what that was, it's an element that's by itself. You need to know what classification it falls into. In the very first unit, no, I'm sorry, in the second unit in here, which we took in order of the third unit because we took one unit out of order to be able to do ice cream. But in the third unit in here, the second unit in here, we classify where chemicals are and what they are by where they are on the periodic table. And so everything from this stair step to this side is a metal, and that's a metal. And except for mercury right here, and actually there's one other, gallium. All these, you don't have to know that. Just to know that mercury is going to be a liquid, okay? All the other metals, if they're by themselves at normal atmospheric pressures and temperatures, this is going to be a solid every time. Okay, we'll start out it being solid, okay? This, we're going to have to look at the solubility rules to find out what its physical state is going to be, okay? So we're going to look and find either magnesium or bromide. And if I look carefully, I'll find that bromide is right here. And it says that bromides are in the soluble section. So most bromides tend to be soluble unless they're bonded with silver, lead, or mercury. So silver bromide would not be a aqueous compound. It would be solid. Lead bromide would be solid. Mercury 1 bromide would be solid. But this is not any of those three. It's not silver, lead, or mercury. So this is soluble. And since there's water around, we said that this is taking place in a water environment, this is going to be aqueous. Okay? All right. So now since we have a metal that's by itself, and we have a compound, the potential exists for this to be a single replacement reaction. But it's only going to happen is if this metal is higher on the activity series and is therefore more active than the part of this compound it's like. And what it's like is this metal ion here, magnesium. Okay? And so we're going to look on this activity series here, and we find that potassium, the K, is right here, and magnesium is right here. The magnesium ion's right here. So potassium is higher and therefore more active than magnesium, so potassium will kick out the magnesium. It will displace the magnesium. So if we were to classify this equation, we'd classify this as a single replacement reaction. Okay? And one of the things you have to do on this test is to classify equations. There are 5 major classifications and 1 subclassification. So under double replacement, you also got acid-base. Although, if you have, if you're forming as a product carbonic acid, which decomposes then to water and CO2, you have to classify that as both double replacement and decomposition. Okay? But that's not really a subclassification. Those two are equal classifications, but the acid-base classification is a subclassification under double replacement. So, potassium is going to kick out the magnesium and join up with the bromine. And the magnesium then is going to be by itself. And then magnesium is a metal, and it's not mercury, so it's going to be a solid. We need to look up and find out about the physical state of potassium bromide. And bromines, we already said, are going to be soluble with 3 exceptions, but this is not one of the exceptions. Plus, if you look at the very first rule under solubility rules, you'll find out that group 1 metal compounds all are soluble without exception. So this is going to be aqueous. Okay? All right. So now we've got to balance this formula. Got to check on the formula, make sure it's balanced. If it's not balanced, balance it. So potassium has a 1+ charge. You go to the periodic table that has oxidation numbers listed on it. If you don't know that already what the charge is, so let me tell you how you can figure out that the charge is what the charge is without that. Everything in column 1, with rare exceptions for hydrogen, everything in column 1 are 1+ charges, or have 1+ charges in an ionic compound. This is a metal bonded with a nonmetal, that's an ionic compound. Everything in this column here, column 17 or 7A, everything in this column here in a binary compound is a 1 negative charge. So I only need 1 of each. So that is already balanced. That makes sense? The whole thing? Say the whole thing over? Okay. Everything in column 1, with rare exceptions for hydrogen, will always have a 1+ charge in a binary compound. Well, anytime. They're always going to have a 1+ charge regardless. All right. 7A. These elements, these halogen elements here. Okay, this is the halogen section. We learned that in Unit 2. All the halogens will always have in a binary compound, and this is a binary compound made of only 2 elements. A binary compound is made of 2 elements, not necessarily just 2 atoms. In a binary compound, these will always have a 1 negative charge. Okay? So there's a 1 negative charge for that bromine. So this is 1+, 1 negative. It's charge balanced. The 1+ cancels out the 1 negative, and so you have a 0 charge overall. Okay, this over here, magnesium, has a 2+ charge. So I needed 2 bromines to balance this magnesium. That's why it's MgBr sub 2. You have a question?
Does it ever matter what order we put them in?
No, it doesn't matter whether this is first or this is first. It never matters. Okay? What is that they call is it the associative property of addition? You know, you can reverse them and still get the same answer. Is that what it is? I'm not a math teacher, so I'm trying to remember which one is which. Commutative, associative, distributive. It's associative, right? Huh?
Yeah.
Anyway, but the point is, no, it doesn't matter. Just like in math, it doesn't matter. Somebody, yes. Okay, no, you cannot put the K with the Mg because they're both metals. Think about it like this. They both have positive charges. Why would they stick together? There's nothing to make them stick together. They don't have opposite charges. That make sense? Okay. All right, now, so we're ready to balance the overall equation. So we're going to list out our elements in an atom inventory. K, Mg, Br. We're going to make our little grid for the inventory. We're going to count everything. I've got 1 potassium on the left, 1 magnesium on the left, and 2 bromines. Over here, I've got 1 of everything. I need to have 2 bromines on the right, and the only way to get 2 bromines on the right is to use a coefficient. Look, once the formula is balanced, and we balance this formula, we said we need 1 potassium, 1 bromine. I can't use coefficients anymore, subscripts anymore. That would be changing that balance. If I were to put numbers in the middle of this, that would change the formula, and that's not allowed. It's not charge balanced anymore. The only thing you can do to balance an equation once the formulas are balanced, and you have to balance the formulas first. Okay, once you have the formulas balanced, you leave it alone. You can only use coefficients to change the number of any number of atoms. Okay, so I've got 2 potassiums now, and I've got 2 bromines. Now that bromine's balanced, I'll go back and balance the potassium by putting a coefficient 2 here, and I got a 2, and everything's balanced. Okay, now, I didn't ask you to do this for homework, but let's write, or did I ask you to do the complete net ion equation? Yeah, I did, didn't I? Yeah, net and complete ion equations. Okay, let's do that. All right, so I'm going to split up anything that's both ionic or acid and is also aqueous. Okay, and I've got 2 of those. This is ionic and aqueous, and this is ionic and aqueous. Everything else is going to stay the same in the complete ionic equation. So in my complete ionic equation, I've got 2 potassiums that I don't do anything to because it's not ionic or acid and it's not aqueous. But this one I'm going to split up. So I've got 1 magnesium, and we just got through saying that magnesium has a 2+ charge. Now you can look on the periodic table here and realize that, oh, everything in column 2 has a 2+ charge in a binary or an ionic compound. Okay? But you could also double check that over here, because here's a periodic table that has oxidation numbers for you. Okay? So that's a 2+ charge, and it's aqueous because the compound is aqueous. And then I've got 2 bromines, and those are negatively charged. And then on the other side over here, I've got 2 potassiums. But now this is not a metal that's solid. This is part of an aqueous ionic compound. This potassium, when it bonded with this bromine, lost an electron and became a 1+ charged ion. Okay? If you remember, this was unit 3 when we learned about that. Okay, and then bromine, we just said, has a 1 negative charge. It gained 1 electron to get a negative charge. And there are 2 of those because of this 2 here. This coefficient 2 means we multiply everything here by 2. Okay? So 2 bromines. And then magnesium doesn't get broken up, doesn't have a charge because it's not, didn't come from an ionic or acidic compound. So that's a complete ionic equation. Then the net ionic equation will only include those things that are not spectators. Okay? The analogy I gave you is if it's in the game, it's going to change. It's going to do something. Okay? If it doesn't change, it's on the bench. It's a spectator. And the spectators we leave out of a net ionic equation. Spectator ions, that's what they're called. In chemistry, they're actually called spectator ions. We leave those out of a net ionic equation. So I'm looking here at potassium, and I've got a potassium with no charge that's solid. Over here is potassium with a charge that's aqueous. Those are not the same. Please be careful. Somebody's going to make that mistake and say, oh, those are the same, and keep them. They're not the same. That changed. It's in the game. So we're going to keep that. 2 potassium, metal, solid. And over here, we're going to keep the 2 potassium ion that's aqueous. It's separate. It's a changed thing. It's not the same anymore. All right, magnesium is 2+ here, and over here is changed. This has a charge. This is an ion. This magnesium lost 2 electrons. This one has all its electrons. So they're not the same. We're going to keep those. Okay. Now here's a bromine. Actually 2 bromines, or bromides really, because they've gained an electron. They got a 1 negative charge, they gained an electron. This is exactly the same. No change. This is a spectator. It's on the bench. It's not in the game. We're going to leave it out of our net ionic equation, and we're done. This is the net ionic equation. Okay? Any questions about that? All right then. Well, I guess while we're here, let's look quickly at this other equation I asked you guys to do. This is 34 on this list. And we had nitric acid. And we had sodium bicarbonate. And it gave you the products, didn't it? Helped you out there. Because you're not familiar with bicarbonate. It is a polyatomic ion, but you might not be familiar with how it's going to react. So it actually gave you all the products here. And we had as a product sodium nitrate. And we have water. And we have carbon dioxide. All right. So this is nitric acid. And if you look on your solubility rules, you'll find that nitrates are always soluble. There's a couple, there might be an exception, but not many. But also group 1 metals, but this is not really a metal, but group 1 it says on the solubility rules, those are aqueous. So we're going to call this aqueous. Or they're soluble if there's water around, and the problem says there's water around. And bicarbonates, it says that sodium compounds. The very first thing on the solubility rule says that all group 1 metal compounds are going to be soluble, and therefore if there's water around, this is going to be aqueous. Okay, and so for the same reason, this is going to be aqueous. And you should know by now that water is going to be a liquid and CO2 is going to be a gas. Water will be a gas if there's lots of heat, and that only happens in combustion reactions in this class. Okay, and so now we're ready to balance the equation. We've got hydrogens, nitrogens, oxygens, and sodiums and carbons, I believe. Okay? Do an atom inventory. Count everything. I've got 1 hydrogen here and 1 here. That's 2. I've got 1 nitrogen here. I've got 3 oxygens and 3 oxygens. That's 6. I've got 1 sodium, and I've got 1 carbon over on the other side. I've got 2 hydrogens here. I've got 1 nitrogen. I've got 3 oxygens and 1 here. That's 4 plus 2 more. That's 6. I've got a sodium and I've got a carbon. And as complex as that equation might look to you at this point in time, it's already balanced. Okay? So the symbol AQ means aqueous. Aqueous means it's dissolved in water. Okay? Now I didn't write the complete net ionic equation here. This is going to split up, that's going to split up, that's going to split up, and these two are not. Okay? Yes?
Can you put in like
Sure. So a complete ionic equation is when you split up those things that are either acidic like this or ionic like this into separate ions. Okay? You keep everything in the equation, but you split up those things that are either in one category, ionic or acid, and in the other category, aqueous. It has to be both those categories to split it up. Okay? So sometimes you have ionic compounds that aren't aqueous, and so you don't split those up.
how you know which one is good?
You just have to know by using this stuff. You know that this is an acid because it's got hydrogen in the front. You know this is ionic because it's got a polyatomic ion in it. And if a compound has when you see a formula like this, you're going to look at that and say, okay, there's more than 2 elements there. I need to look on that common ions list and see if there's a polyatomic ion there. Okay? Everything I give you so far has had a polyatomic ion in that situation. It doesn't happen always with organic compounds, but we didn't get that far in organic compounds. In organic compounds, all we did were the hydrocarbons, hydrogens and carbons. So if you have more than 2 elements in a formula, you're going to look for the polyatomic ion. And the polyatomic ion's presence tells you that's an ionic compound. The other kind of ionic compound, at least in this case, is when you have a metal bonded with a nonmetal. You know it's ionic. So if it's acidic or ionic, and it's also aqueous, acidic aqueous, ionic aqueous, either one, if it's one of those, you're going to split it up. If it's not, you're not going to split it up. So when you write the complete ionic equation, you're going to have the aqueous acids and ionic compounds split up, and you keep everything else the same. And in the net ionic equation, you just get rid of the things that stay the same on both sides, the spectator ions.
You stick them out.
Take them out. Yeah. Yes?
Don't we have to write the
Yeah, if you have to split it out, there better be charges on there. Okay, because there are charges, okay? They're ionic compounds. When you split them up, you're splitting them up into separate ions. Yeah, you're going to leave the H2O and the CO2 alone because they're not acidic, they're not ionic, they're not aqueous either. Okay? So you're not going to split those up. There's not going to be charges on these at all. When you split this up, you'll write that as sodium with a 1+ charge, and the nitrate polyatomic ion stays together. Polyatomic ions tend to stay together, both when you're writing the products over here and when you're splitting it out into ionic equations. Okay? So the nitrate has a 1 negative charge. You have to write that down there when you write the nitrate separately. Okay? It's just undoing the stuff we learned to do when we're balancing these compounds in the last section, the last unit. So you guys have a class website, and we're going to go here under all chemistry classes. This is www.heterochemistry.com. We're going to go to your class, and your class is Chemistry 1 Advanced. We'll click there. It's going to take us to that page, and we're in Unit 5. So I'm going to scroll down until I find Unit 5. And there's 4 and there's 5. Okay? And so Unit 5, here's the Unit 5. It says CP because Advanced used to be called CP. I haven't gotten around to changing those yet. But you can download the entire text for this unit. Okay? Click that down there, and the whole text is going to pop up. And so you can find all kinds of things in here that's going to explain all this to you. Complete net ionic equations, all the different types of equations and their classifications, how to determine physical states, all that's in there. And under each section in here, there are very often practice questions. Okay? Now, not all the answers are there, but sometimes there are answers there. But let's go down to the very bottom. All right, so here's that list of problems I showed you yesterday. We picked some problems out of those, okay? And no, I didn't include the answers to that in there, okay? But now, if you go to these sections and pick one of the problems that start for you, it'll walk you through these step by step. Let's say you're working with, let's see here. Let's go with this one right here. Okay, here's a reaction, here's a problem. Okay, well, not that one because that one doesn't do anything. Okay, here's one. Okay, right here. And it walks you through the whole thing, how to write the complete ionic equation, all the steps you go through. Let's see. Oh, that's for ionic equations, isn't it? Combustion reactions shows you previously. There's places that show you how to go up balancing equations. So if we're up here, it shows you how to do that. Okay, everything's there. All right. But I'm sure if you go on the internet, you can find lots of problems with solutions listed for you. If you need me to give you a link, just email me and ask me for a link, and I'll give it to you. Okay? But it's not hard to do. Just type it in a search engine, practice with chemical equations, or practice predicting the products of chemical equations, or something like that. And it should bring up lots of those worksheets. A lot of people do stuff just like me and put these things on the internet. Okay? Yes?
So the next time we come to these notes, it's going to be Monday?
Might actually come to these on Friday, depending on some other things, because this lab on Friday is going to carry over. It kind of ties this unit into the next unit. Stoichiometry is the kind of math you do in chemistry that requires a balanced chemical equation. So let me give you just a quick look at what that looks like. Okay, so here is an equation we just balanced. All right, this is one of the homework problems. And let's say I ask this question. If, and it applies to this equation, if 2.50 grams of potassium is reacted with an excess. An excess means you got more than you need, okay, of aqueous magnesium bromide. So if I were giving you this problem without this equation already for you, you have to figure it out from what I'm writing there. This is potassium right here. This is magnesium bromide right here. All right. Then how much magnesium will be produced? Okay. That's a stoichiometry question. Now, there's a lot more to it than this, but basically without this balanced equation, you can't solve this problem. So I'm going to set it up for you. We're not going to solve it. We've only got time just to show you how it's going to be set up. So 2.50 grams of potassium goes here. I need a molar mass. Please pay attention. A molar mass for potassium. Potassium's molar mass is 39.0983 grams of potassium for every mole of potassium. Okay? And then I need a molar ratio from this balanced equation. This is why stoichiometry requires a balanced equation. If the equation is not balanced, you can't do the stoichiometry correctly. And I have 2 moles of potassium here on the left. I'll put that 2 moles of potassium on the bottom here, the 1 mole of magnesium on the top here. And then, in order to find out how much, I've got to convert moles to grams, and I'll use the molar mass of magnesium. So 1 mole of magnesium is equal to 24.3050 grams of magnesium. Okay? And where did I get those numbers from? They're on the periodic table. That's the atomic mass in grams. That's all it is. Okay? And so when I solve this problem, guys, I didn't say pack up yet, guys. Please stop milling around, packing up. We got a minute. Okay? Grams cancel, potassiums cancel. Moles cancel, potassium cancels. Moles and magnesium cancel. And all I got left is magnesium and the mass, and that's what I'm looking for. And this is the process of dimensional analysis. So all that stuff in Unit 1, where you learned about conversion units and canceling out units in dimensional analysis, it comes back again. This is where we're going to really use it. Okay? So the way that you use the activity series of metals for single replacement reactions is pretty simple. Any metal by itself in an equation can potentially displace a metal ion in a compound. But whether it will displace it has to do with where it's on here. Now metals can also displace hydrogen in an acid. Okay, that's down here. And halogens can displace halogens. So when I use a phrase like an element that's by itself has to be able to displace something it's like, by that I mean that metals can displace metals or hydrogen in an acid, and that halogens can displace halogens. But the whole thing is, if it's by itself, it has to be higher than what it's like in the compound, whether it's in the metal hydrogen column or the halogens column. Okay? So let's do an example here. Let's see. Actually, I gave you a problem for your homework, didn't I? So the 2 highlighted problems here, what I assigned for homework, and the first one just happens to be a single replacement reaction. Okay? All right, let's pay attention here. All right, so this is happening in water. Okay? So you have to use the solubility rules to find out if this ionic compound is aqueous or not, but this is a metal. And except for mercury, in here at least, there is one other element, but except for mercury, all metals are going to be solids. So we're going to write S right here. And then we're going to look at the solubility rules for this compound. And we see, if we look right here, that bromides are soluble. So if there's water around, and I said there is water around, if there's water around, then this bromide compound ought to be soluble unless there's an exception. Okay? Well, magnesium is not one of the 3 exceptions. The 3 exceptions are bromine, or bromide bonded with magnesium, or bonded with lead, or bonded with mercury 1. So that's not an exception, so this is indeed aqueous, okay? Soluble means it can dissolve. If there's no water around, there's nothing for it to dissolve in, so you still call that a solid. But if there is water around, then it's going to be dissolved, and we're going to call it aqueous.
I thought we only did this for the other side. Okay.
All right, so now we can look and see that we have a metal by itself. And if a reaction is going to happen when you have a metal by itself, or a halogen by itself, or even hydrogen gas, although that's not really typical, this metal has to displace something it's like in the compound. And like, the word like in that phrase, means that there has to be a metal ion in the compound. So metals can displace other metals. Metals can sometimes displace hydrogen in a gas, hydrogen in an acid, and halogens can only displace other halogens, okay? But this is a metal displacing a metal, but it's only going to happen if the metal that's by itself is more active than the metal in the compound. And the way that you know it's more active using this activity series is that it ranks higher on the activity series. And so potassium, the K, the potassium is right here. The magnesium, the metal that's in the metal ion that's in the compound, is down below it. So potassium is higher and therefore more active than magnesium is. So it will displace the magnesium, and you do have a reaction. If it wasn't higher, you just write NR and you'd be done. But since it's higher, we have to do all the other stuff that's required, and that starts with predicting the products. So if potassium then goes with bromine, that's what happens when potassium displaces the magnesium. It joins up with the bromine and kicks out the magnesium. Okay? And so magnesium is going to be by itself. Now, this subscript doesn't travel. The only subscripts that actually travel automatically to the other side of the equation are those that are actually part of the formula for a polyatomic ion. And this is not a polyatomic ion. It's a monoatomic ion. There just happens to be 2 bromines for every magnesium, because magnesium has a 2+ charge, and bromine in a binary compound like this has a 1 negative charge, and it's called bromide when it gains a negative charge. All right, so now that we've figured out what goes over here, we can start figuring out how to balance those formulas and how to figure out the physical states. Now this is now a metal by itself, and so it's going to have a solid physical state. And we just said bromines, for the most part, are going to be aqueous, and there's no exception for potassium. So you kind of should know, if you didn't remember, that's okay, you can look it up, that this is going to be aqueous. But it also turns out that the very first rule, under solubility rule, says group 1 metal compounds are always soluble, no exceptions. So for 2 reasons, you should be able to figure out that this is aqueous. Okay?
I have a question too.
All right, so now we need to figure out how to balance this compound. And so you can do it a couple of different ways. One way is that potassium's right here, and it says it has a 1+ charge. Okay? And bromine just happens to be here. It isn't always going to be down here, but it has a 1 negative charge. Another way to do that is to go to your periodic table. And this is one you should know, even though we're using other tools, you should know that all the elements, with rare exceptions for hydrogen, all the elements in column 1, all these alkali metals here, they always have a 1+ charge in a compound, okay? And all the elements in column 7A or column 17 of the periodic table, these halogens, always have in a binary compound a 1 negative charge. So that's a second way to know it. And a third way to know it is to just look it up on this periodic table with oxidation numbers. I just happen to give you that. So if you're looking at the halogens here, and you're saying to yourself, okay, bromine has 4 different charges. Well, potassium only has a 1+ charge. So what kind of charge does chlorine have to have if your compound is going to be neutrally charged when you're done? It's got to be some kind of negative charge. It could be 1 positive, 1 negative, or 2 negative or something, but the only negative charge for bromine is 1 negative. Okay, that's how you know. All right. So if potassium has a 1+ charge and bromine has a 1 negative charge, then I need one of each to have a neutrally charged compound. A neutrally charged compound means the compound has no charge. The plus charges or positive charges sort of wipe out the negative charges. Okay? So that's balanced already. Now we're ready to go about balancing the equation. And we have to use an atom inventory. In this class it's required. So we are going to list, first of all, everything we have in the equation. So we've actually gone to answering your question already about how you use the activity series. Does that cover it for you? Okay. Now, we're only using metals in this equation, but you could have halogens replacing halogens. Okay, so be careful about knowing you can do both of those. All right, so we're going to count all the elements we have here. We have 1 potassium, we've got 1 magnesium, but this subscript 2 means I have 2 bromines. And then over on the other side, I've got 1 potassium, and I've got 1 magnesium, and I've only got 1 bromine. Now, once these formulas are balanced, you can't add anything to the formula itself to try and balance an equation. You can't stick a number in the formula. You can't put like a 2 here, because that would change the formula. That means that formula, if you put a 2 here, would have a 1 negative charge. And we don't want it to have a 1 negative charge. We want it to be neutrally charged. Okay? The only way you can balance an equation after all the formulas are balanced in the equation is to use coefficients, which change the number of everything in that formula. So if I put a 2 here, which is what I need, that means I have 2 potassium bromide units, formula units, and if I'm putting that in my atom inventory, that means I have 2 potassiums and 2 bromines. Okay? Now then, I got to go back to the other side and look at how to get potassium to be the same number, and so I'll put a 2 here, and I'll have 2 potassiums. And the equation's balanced. Now, that's just balancing the equation. Okay? Up until yesterday, that's everything we've done with this. And then yesterday, we learned to do a new process, which is really not a lot new. It's just undoing something you learned to do in the last unit. So we take any of the ionic compounds or the acid compounds that are also aqueous, and we break them apart. And we're going to do that process to write what are called complete and net ionic equations. So now, what I want to look for are any formulas in here that represent either ionic compounds or acids, but they, in addition to being either ionic or acid, they also have to be aqueous. Okay, because occasionally you'll have an ionic compound that's not aqueous. If you go to the solubility rules and you figure out that something is not going to be soluble, and you have that compound in your equation, then that's a solid. It's not aqueous. And so if I have an ionic compound that's a solid, it doesn't break up. It's only the aqueous ionic compounds or the aqueous acidic compounds that break up. Well, this is a metal by itself. It's obviously not an ionic compound, so it's not going to break up. We're just going to write it exactly the way it appears in the equation. Now, this is an ionic compound. I've got a metal combined with a nonmetal. And that's one way you can tell if you have an ionic compound. There are some ionic compounds that are not metals bonded with nonmetals exactly, but they do contain a polyatomic ion. So that's the other way you can tell they have an ionic compound. If there is a polyatomic ion in the formula, then you know you have an ionic compound. And if you have a formula that has more than 2 elements, your first thing to do is to go and look on the common ions list and find that polyatomic ion formula. Okay, and make sure you've got that identified and know what it is. All right, now, so this is aqueous and it's ionic, so it does break up. So we're going to split that up. Now, before, this was already written for you, but if you were balancing a compound that contained magnesium and bromine, you would have found that magnesium had a 2+ charge and bromine has a 1 negative charge. Okay, and that's all you got to do. You got to know that and write it out as a separate ion. So there's 1 magnesium here, and it has a 2+ charge. Now, if you didn't know that, where would you look?
The other chart.
You could figure it out maybe from looking at the activity series. It might be there. You might find it on the periodic table with oxidation numbers. You would find it there. But you can still figure that out just from the regular periodic table. You don't need the periodic table with oxidation numbers to figure out the charge on magnesium because it's in column 2. And all column 2 metals have a 2+ charge. All right. So we have 1 magnesium, and if this thing is dissolved, the reason it's dissolved is because it actually does split into ionic charges, separate particles. Okay, so we'll find that out when we get to the solutions chapter. That's the way it actually dissolves. Is ionic compounds actually break apart into separate ions. So if this is aqueous, the ions have to be aqueous because they're what's actually in the solution. So we're going to list this as being aqueous. And so the 2 bromine ions, or bromides, the 2 bromides, are also aqueous because that's how it actually dissolves when it's an ionic compound or it's an acid compound. When it is dissolved in water, it actually does break up into separate ions. Well, that's not an absolute. There are actually some acids that don't do that. And like I said, there are some ionic compounds that don't actually form aqueous solutions. They remain solids. But that's kind of what we're doing here. If we're aqueous and ionic, we're going to split it up. All right, so here, this is the same thing. This is ionic and it's aqueous, so it's got to split up. And I have 2 potassiums and 2 bromines. But this potassium is not potassium, the metal, like the one on the left here. This is a potassium ion. It's a charged particle that's attracted to the bromine that has a negative charge, making it an ionic compound. So if this breaks up, it's aqueous. We're going to list it as aqueous here because that's what it actually does when it is put in solution. And we've got 2 bromines or 2 bromides. And then this magnesium on the end, it's not aqueous, it's not acidic, it's not ionic, so it's going to stay the same. It's not going to change at all. All right. Now, potassium and magnesium actually have a 0 oxidation number. Elements that are by themselves in nature that don't exist in some ionic form like this, they actually have a 0 oxidation number. We don't write the 0, but I mean it would be okay if you did. It wouldn't violate any rules if you wrote 0 there. All right, so that is a complete ionic equation, okay? Complete ionic equation. Now, for the net ionic equation, we're going to get rid of the bench sitters. Okay, the analogy I used yesterday was we're looking for the spectator ions. And the spectator ions, I said yesterday, are kind of like the people that are not in the game. Okay, they're not on the football field, they're not on the baseball field, they're not on the basketball court. They're actually sitting on the bench, so they're at, they're not at that particular time anyway. They're not in the game. Okay, they're spectators, and we're going to get rid of the spectators. A net ionic equation only shows the ions that are in the game. Okay, so well, we're going to look at this. So here's a potassium, and it's a solid that has no charge. That's not the same as this potassium with a charge that's aqueous. So this is changing. We're going to keep both those. If it's changing, you keep it. This magnesium ion has a 2+ charge. It's aqueous. This is magnesium metal. It's not an ion. It's a solid. It changed. So we're going to keep it. Or keep them, I guess. Okay? Now these bromine ions, they're exactly the same. I have 2 Br negative aqueous on both sides. It's exactly the same. It didn't change. If it's not changing, it's on the bench. It's not in the game. It's a spectator. We leave it out. That's the net ionic equation. We're done.
Which one is it, the top one or the bottom one?
So the complete ionic equation has the spectators. The net ionic equation doesn't. All right? All right, so we're going to look at the second equation, number 34 on here that I highlighted. All right, here. So here's that other equation I asked you to do for homework. I guess since I've already given you the products here, okay, you didn't have to figure out the products. And the reason for that is we haven't talked about how this polyatomic ion here works as far as the solubility rules and how you use that to predict products and things like that. So when I gave you the answers over here on this. But this, we do know that this is going to be aqueous, and even if you didn't know, well, this is a carbonate, you could look it up that way. It is a sodium compound. And on the solubility rules, it says group 1 salts. Well, if it has a metal in column 1 of the periodic table, that's a group 1 metal. And if it's in an ionic compound, that's a salt. Okay? So that's a group 1 salt because I've got a group 1 metal right here, and I've got a polyatomic ion, so I know it's an ionic compound. Okay? So this is aqueous. And this one is a nitrate compound. And let's see here. Nitrates. All nitrates are always soluble. Okay? So this is going to be aqueous. This is a nitrate compound, and it's a group 1 metal salt, so that's aqueous. There's no heat around, so water, in the absence of any heat, is going to be a liquid. And what physical state are we going to assign to carbon dioxide? Gas. Okay? So we're ready to balance the equation now. So we're going to list all of our elements. We've got hydrogens, nitrogens, oxygens, sodiums, and carbons. And we're going to make a grid here.
How did you determine that it was the first one?
Because nitrate compounds, it's rule number 1 under the solubility rule, says nitrate compounds are always aqueous. It's right here, nitrates.
My bad.
Okay? All right, so we're ready to count all of the atoms we have in our equation. So I always ask you guys to put this vertical line underneath the arrow, because what I want to do is divide the left-hand side of the problem from the right-hand side. I won't count off if it's not there. I've just found by experience that students make more mistakes when they don't do it that way. So put the vertical line there, and just remember that everything on this side of that vertical line is everything over here, and everything on the right-hand side of this vertical line is everything over here. So now we're going to count everything. I've got 1 hydrogen here and 1 here, so I'm starting out with 2 hydrogens. I have 1 nitrogen. I've got 3 oxygens and 3 oxygens here, so that's 6 oxygens. I've got 1 sodium and 1 carbon. So when you're counting these up, don't forget to count all of those elements, okay? So if you count them one time and say, let's just say you didn't realize there was an oxygen over here, you counted these 3. When you got over here and saw 3 there, you should realize at that point, well, there should have been, you got to count a double set. So make sure you keep up with that, okay? So over on the other side, I've got 2 hydrogens, 1 nitrogen. I've got 3 oxygens here, 1 here, and 2 here. That's 6 oxygens. I've got a sodium and 1 carbon, so that's already balanced. Okay, so you didn't have to really balance this one, but you do have to show me the atom inventory because I'm from Missouri. All right. Not really from Missouri, but that's just what I say because that's what happens when you're from Missouri. Well, look it up. Go to a search engine, type in show me and the word and the state Missouri, and see if you can figure. Not now on your cell phone. You're not supposed to be using your cell phone in here. No, do it at home. Write a note to yourself. All right.
What if you use it later?
Now we're going to write the complete ionic equation. All right. So this is an acid, and it's aqueous. So acids that are also aqueous split up in a complete ionic equation.
How do you know it's acid?
Because it's got hydrogen on the front. That's how you know it's acid. All right, so I split it up. And here, I've got sodium. And if you didn't know, you should look this up. That's called a bicarbonate ion. Okay, HCO3 is a bicarbonate ion. Look it up on your common ions list. If you know that this is carbonate, but you know you have 2 other elements, you need to be looking to see if there's another ion. Okay, make sure you got the complete ion here. This is a polyatomic anion. Anion for negative, polyatomic because there's more than 1 atom. Okay, so we've got a sodium here, which has a 1+ charge. Since this whole compound is aqueous, the sodium ion is aqueous.
Can you move it up?
And you've got a bicarbonate ion. Okay, and over here we've got an ionic compound, and it's aqueous, so we're going to split it up. So acids that are aqueous and ionic compounds that are aqueous are the only compounds that split up, and they have to be both acid or ionic and aqueous. So the solid ionic compounds don't split up. So these polyatomic ions tend to stay together. Whether I'm taking and putting them over on the right-hand side to just predict the products of an equation, or I'm making them into these ionic equations, these complete or net ionic equations, polyatomic ions tend to stay together. Now in reality they sometimes don't stay together, but your first assumption is, your first hypothesis is they will stay together, okay? So if we're looking for this right here, and we want to know its charge, all we got to do is find the bicarbonate ion. It's right here. Now it says hydrogen carbonate here, but if you look underneath in the little letters, it says bicarbonate. is a widely used common name. Okay? So this stuff right here, sodium bicarbonate, you probably have that in your kitchen right now. All right? So this is going to split up. We're going to split it up into sodium and nitrate ions. And then the water doesn't change, and the CO2 doesn't change because it's neither ionic or acidic. Okay? So that's a complete ionic equation. If you were to run this reaction, this is what would be actually exist in the water. Well, except for the CO2, which will be bubbling out. So we want to write a net ionic equation now. And to do that, all we got to do is figure out, well, what are the spectators? Well, let's look at hydrogen here first. This is H plus aqueous. There's no H plus aqueous on the right-hand side. There is H in the water, but that's not the same thing. It has to be exactly the same. Exactly the same in charges, exactly the same in its physical state. Okay? So that's going to stay, and the water's going to stay. All right. Now, here's a nitrate ion, NO sub 3, superscript negative, AQ in parentheses, and there's a nitrate ion over here, exactly the same. Those are spectators. We're not going to include those. They're sitting on the bench. Here's a sodium ion, Na plus aqueous, excuse me. And there's also a sodium ion over here. Those are exactly the same. Same charges, aqueous, everything's the same. If anything were different on either side, you would keep them both, but they're exactly the same. They're bench sitters, they're spectators, we're leaving them out. Okay? And here's this bicarbonate ion. There's no bicarbonate ion over here anywhere. So we have to keep the bicarbonate ion. Over here on this side, there's a CO2 we didn't account for. There's no CO2 on the left. There's HCO3 negative aqueous, but that's not the same as this. This is CO2 with a gas physical state symbol. Okay? So there's nothing that's like it over here. We're going to keep the CO2. All right? And that's the net ionic equation. So the question was something about combustion reactions. Not something about, but when I go over it again. Now listen, let me be clear about something, okay? On the test, don't expect me to label what equations fit what category, what classification, okay? There are 5 major classifications of reactions. You have to be able to look at those and determine what the classification is, okay? But I was asked about combustion reactions, so I'm going to show you a combustion reaction, okay? Actually, you know, I should have left that blank. How do I know that's a gas? We do know. It's not just carbon, because I said yesterday how you know it's a gas when it's a compound that has 3 carbons. 5 or less, yes. If the chain of carbons, if it's a straight hydrocarbon, and a chain has 5 or less carbons, that's going to be a gas. And I said between 5 and 15, not including 5 and 15, but between 5 and 15, we're going to say that's a liquid. And then we're going to say 15 and over is a solid. That's not always true, but that's what we're going to call it in here, just to kind of make it easy. Those are easy round numbers to remember, and they're, you know, pretty good. Yes? We covered the definition of a combustion reaction in Unit 10. And we said then that a combustion reaction is any reaction in which a fuel of some kind, that's a chemical, a fuel is a chemical, a fuel of some kind reacts with oxygen And then besides the chemical products, it also produces light and heat.
So since that's between section,
Now, while any reaction with any fuel and oxygen that also produces, besides chemicals, produces light and heat, that's a combustion reaction. In this class, we've narrowed our focus for combustion reactions. In this class, the only combustion reactions we are going to be using is a combustion reaction that starts with a hydrocarbon fuel. Okay? So for this class, our combustion reactions will have a reaction between a hydrocarbon fuel and oxygen. And for those kinds of combustion reactions, we're always going to have the same products every time. Carbon dioxide and water. Every time. Carbon dioxide and water. Now, there are some reactions that produce carbon dioxide and water that aren't combustion. But if you have all the conditions, hydrocarbon fuel, reacting with oxygen, you're always going to produce water and carbon dioxide, and there's also light and heat. And we're not really dealing with the heat right now, light and heat, because we did that in Unit 10, and we took Unit 10 early so we could eat ice cream, right? Okay, because that was thermochemistry. We wanted to eat ice cream before it got cold. Got that? All right, now.
Yes.
So, on a test, really, you should know this anyway. You might only get this. You might not even get the gas here, the gas symbol. All right, you might just get this chemical symbol and this O2, and you have to do the rest. Okay? Because you're capable of doing the rest. Okay? Now, so you should know what the physical state of oxygen is. That should be pretty easy. Gas.
oh snap!
Okay? That's okay.
But I thought it would be a
All right, now, if I am reacting a hydrocarbon fuel and oxygen, I just told you, what are the products always going to be? Huh? Carbon dioxide and water. Every time. This is the easiest kind of reaction to predict the products for, because it's always the same. There's no moving things around, no trying to figure out whether something replaces something. It's just carbon dioxide and water. If you identify hydrocarbon and oxygen, carbon dioxide and water is going to be the products. Okay, what physical state is CO2? Why? Because it is. You just have to know that. Carbon dioxide is always a gas at atmospheric pressures and temperatures. You have to get it really, really cold or under an awful lot of pressure to get it to be anything other than a gas.
Would it be a solid if it's cold?
If you got it cold enough to be a solid, yes. As long as the atmospheric pressure is about 1 atmosphere, which is what it is in our atmosphere, okay, near the Earth's surface anyway, you'd have to get it really, really, really cold to get it to be anything else, okay? All right, now if you put it under a lot of pressure, you can make it become a solid at a little bit higher temperature, but not much. But it'll never be a liquid without a lot of pressure, period. All right, now, water. Water has to have heat to be turned into a gas. And this is the kind of reaction that produces light and heat. So this is going to be
Liquid. Oh,
Gas.
gas.
Wait, there's no color in that one. There's no color in that. When I asked you about that water, and you said.
All right, now that we've figured out what the products are, now that we've figured out what the physical states are, we're ready to balance the equation. And we have to use
Balancing.
atom inventory.
Shut up.
Come on, I've been saying this forever. Really?
So,
Atom inventory.
Atom inventory. What was the question? You said atom inventory.
The balance.
Oh, it's called.
Can I read it again?
All right. Please pay attention. Please. Please. I know you're trying to help, but just turn it down a little bit, okay? You can help and still not interrupt, okay? All right. So we got 3 carbons, 8 hydrogens, and 2 oxygens on the left. I've got this vertical line under the arrow so I can keep up with the fact that all these things over here on the left and all these things over here on the right, okay? And on the right-hand side, I've got 1 carbon, I've got 2 hydrogens, and 3 oxygens. And what I need to do is to fix this so that I've got the same number of carbons and hydrogens on both sides. But these formulas are set. Once the formulas are set, once they're balanced, you can't mess with the formulas. You can change the number of formulas, but you can't change the numbers in formulas. Okay? All right, so we've got 3 carbons on the left, okay, and we've got 1 carbon on the right. To get 3 carbons on the right, I need to put a coefficient. That's changing the number of formula units without changing the formula. Coefficient 3, that's going to change the number of carbons. It's going to change the number of oxygens. Okay?
Why would you put it there?
Because you gotta balance it thing out.
Cause.
This is going to give us then
Yep.
3 carbons here, and we're going to count the oxygens. Guys, don't try to save on pencil graphite. Write it out. I know the math seems awfully simple, but when you've got a little bit of multiplication here, a little multiplication here, a little addition in between, you know, it's kind of hard to keep up with all that when you're trying to do everything else for the first time. So make sure you write it down. I've seen lots and lots of students make mistakes on this because they just didn't want to use the pencil lead. Write it down. Write it out so you can see what's going on. Okay? Huh? It's graphite.
The lead, you said pencil lead.
Did I say pencil lead? Well, you know what pencil lead is. It's graphite. Okay. All right. 3 times 2 oxygens, that's 6. And 1 oxygen here, that means I have 7 oxygens. All right, now I've got 8 hydrogens on the left, 2 hydrogens on the right. To get 8 hydrogens on the right, I need a coefficient 4 here.
Wait, Mr. Tedder. No, he won't stop. I don't want to stop when I ask for 3.
That's going to change the number of hydrogens and oxygens. All right, so now I've got 4 times 2 hydrogens, that's 8. I need to count up all the oxygens. I've got 3 times 2 here, that's 6 oxygens. I've got 4 times 1 here, so that's 4 oxygens, so I've got a total of 10 oxygens. Okay? So 10 oxygens. All right, now, this kind of makes things easy because, you know, sometimes we have to multiply everything by 2. We don't have to here because all I got to do is have a 5 here to get 10 oxygens to match both sides.
Now you don't have. Oh, okay.
Okay?
So what did you do? You put a 5 right there.
No. All right. So generally speaking, if I have straight chain hydrocarbons, if I have an even number of carbons in the hydrocarbon fuel, I'm going to have to do that multiplied by 2 thing. If I have an odd number of carbons in the hydrocarbon fuel, I won't have to do that multiplied by 2 thing. If you have an even number of oxygens on the left and an odd number of oxygens on the right, the only way to get it to work out is to multiply all the coefficients except the one in front of oxygen by 2.
Is that going to be a carbon?
Sorry, carbons, not oxygens, yeah. Okay, the only equations for which complete and net ionic equations can be written, at least in this class, are the single replacement and double replacement reactions. That's it. Now, do you have to do it for everyone? You only have to do it on a test if I ask for it. Okay? All right. There's synthesis reactions. There's decomposition reactions. There's single replacement reactions. There's double replacement reactions. And under double replacement, you've also got the category of acid-base. And you've got combustion reactions. So 5 categories. 5 major categories and 1 subcategory. Now listen, there's also an occasional equation that comes up that we talked about yesterday where you have 2 classifications in one reaction. If I have a double replacement reaction and one of the products is carbonic acid, that automatically, immediately decomposes into water and CO2. So if I have a double replacement reaction that produces carbonic acid, you're going to have to classify that as 2 ways, double replacement and as decomposition, okay? Carbonic acid. Carbonic acid. Acids are named for the anion. The carbonic acid anion is carbonate. CO3, 2 negative. So I need 2 hydrogens on the front. That's H2CO3.
You gotta change it.
That one automatically decomposes into H2O and CO2. The law of conservation of matter states,
Neither created nor destroyed.
right, matter is neither created or destroyed in a chemical reaction.
This is what I get confused on trying to predict the reaction.
Okay? If, I don't have a protractor. I can put my hand on right away.
Not teach for
For chemistry, you need a protractor?
no, a printer. I need a printer. Like, I need a.
I can't do that. I can't do that right now.
I
All
said
right.
after class.
Maybe after class. Okay. Now, children. Quiet, children.
Kid.
Quiet, children.
Shut up. Dang. Adult lad.
All right. It would be okay. You are hindering instruction, and that's pretty important. I don't want to hear what you're doing. I'm saying you're hindering instruction. If you keep talking when I'm trying to teach, you are interfering.
Like you're being a hindrance.
Charlotte, that's what you're doing right now.
Actually, I was trying to
Charlotte, Charlotte,
I got a question.
Charlotte,
my name on the video code.
Exactly.
Charlotte.
I got a question.
Does it have to do with this?
Yes.
Okay.
I've been trying to ask you.
All right.
Talk to somebody else. I think you have a question. I'm trying to figure. No, I'm not lying. Shut up. You said, I need help with like the first one.
The first one. What?
Like in the soluble list it says chloride and chlorate, but I forgot how to name an acid. Isn't it hydro?
Okay. Well, you don't have to name acids in this unit.
But don't you have to start off at naming it as ion compound? And then
But you have to be able to identify the ions, yes, because that's part of the solubility rules.
the hydrochloride.
If it says if it's a chlorate ion, you just have to be able to identify it's a chlorate ion. That's all you have to do to be able to use the solubility rules.
She doesn't know whether
If it's a chlorate or a chloride.
Well, look on the common ions list. It's written right there.
But that's what I was looking at, and I didn't see that formula. Why we gotta have these, Brett?
All right, let's see. You're looking for chlorate. Chlorate's right. There's perchlorate. I'm sorry. Chlorate. Where's chlorate? There's chlorate right here. Chlorate's right here. Perchlorate's right here. Chlorite's right here. Hypochlorite's right here. Chloride, any IDE endings like that, that's a monoatomic ion. That's a chlorine atom that has gained electrons.
But I was looking for HCl.
Huh?
she's talking about HCl.
Yeah, I'm talking about HCl.
What about it?
How do you know if it's
Yeah.
Okay, well, it's not chlorate, it's not chloride, it's not perchlorate, it's not hypochlorite because it's not on here.
Yeah, and that's why I was trying to figure out what to determine. Is it a solid? Because it's not. Either the ones on this list.
Well, chlorides are on the list. Chlorides are right here.
Yeah, and that's what I'm saying. I didn't know if this was a chloride or a chlorate because they're both
Oh.
on the list.
Gotcha. Well, it doesn't have oxygen. It doesn't have oxygen.
Yeah,
So it's not chlorate.
and it's not a chloride either.
It is a chloride
How do I know that? That's what
because
I'm saying.
it's a monoatomic ion. It's not a polyatomic ion. Monoatomic ions that are negative have IDE endings.
So.
What is a monatomic ion?
What is that? Is that not an acid?
Yeah.
This is an acid, but it's an acid because it's got hydrogen on the front.
Yes, that's what I was.
Okay, but what if chlorine was with
I was
something
asking
else?
you, Mr. Taylor.
Would it still, if it was like just chlorine, or was it like chlorine 2 or chlorine 3? If it's just chlorine with something else, it would still be chlorine.
If it's chlorine with oxygen, it's got to be one of those polyatomic ions.
Okay, well,
then it's just chloride.
CLO would be a chlorate, right?
ClO with no subscript is a perchlorite. I'm sorry, hypochlorite.
Okay, listen.
Yes.
It's a chloride
Okay. That's a chloride.
because it's a monoatomic ion,
Correct.
meaning that it's not on the list of polyatomic ions.
Yes.
Okay, so if it's not polyatomic ion, it's a monoatomic ion.
If it's an ion, it's not polyatomic, yeah.
If it's not I knew what I was about to say. I can't word this the way I want to because
Okay. I understand.
If it's not a monoatomic ion, well, no, that's not it. If it's not a polyatomic ion, then it's a chloride.
In this case, yes.
Okay, so it's soluble, which means it's aqueous.
Yes.
God,
Can you explain the monatomic ion?
I was stuck on that like for the longest.
Okay, a monoatomic ion is a single atom that has gained or lost electrons. It has a charge. A polyatomic ion is more than one atom bonded together covalently, and the overall structure has a charge. Yes,
Okay, so just because it doesn't have a charge, that's what makes it a monatomic.
because no.
I mean, the equation you got right there, the HCl, it doesn't have a charge. So
Right, but this is because this has a positive charge and this has a negative charge, and they cancel each other out. If you split them up, this has a positive charge and this has a negative charge. Yep.
So when you put a polyatomic ion together, it has its own charge.
Yes.
Is that what you're saying?
Yes.
Okay.
All right. Yes.
Okay, so the second one would be aqueous, right? Because the one is carbonate, but it says when it's with the other blah blah blah, this is what the NH4 is, right?
Correct. So carbonates are insoluble, but not when it's bonded with ammonium. So this would be aqueous. Okay. Now, you would benefit most if you would first stop talking to other people. Second, stop texting on your phone. Third, stop paying attention to things other than chemistry. Fourth, dig it out in a small group, like 2 people, and figure this out for yourself. If I show you as a class, you don't get as much out of it. You're not as prepared for the test. Okay? So the question is, do you want to dig this out for yourself, or do you want to be passive and have me show it to you?
May I ask you, do you know what I'm saying? It's, what is this, what is this equation represent? Is it like,
You have to finish this equation. That's what it represents.
because I have to put it in my category, so I'm not ever asking this again.
It's no category, because you have to figure that out. You have to figure out what it's going to be.
They are soluble, except what's about the insoluble, soluble, NH4?
Okay? If it's quick.
Carbonate.
All right. So this is an acid, which means for our benefit right now, we'll consider that being an ion bonded to another ion, a positive ion and a negative ion. So this is an ionic compound in this context, and it's aqueous because chlorides are soluble, with a few exceptions, and hydrogen is not one of those exceptions. So this is aqueous. All right. Now, this is soluble for 2 different reasons. One of the reasons is it says ammonium compounds right here are always soluble all the time, no exceptions. All right. Carbonates, it says down here, are insoluble unless they're bonded with ammonium. So this is also aqueous for that reason. Okay? Now, in terms of what kind of reaction we're going to have, this is an ionic compound in this context. It's an acid, which we treat like an ionic compound for our classification, 5 classifications. Okay? This is an ionic compound because it contains a polyatomic ion. You can identify an ionic compound if it's either metal-nonmetal combination or it contains a polyatomic ion. Since it contains a polyatomic ion, it's ionic. If I have 2 ionic compounds, or an acid and an ionic compound, the most likely reaction is double replacement. So the front part of this goes with the back part of this. And the front part of this goes with the back part of this. Now we need to balance the formulas. Hydrogen has a 1+ charge, and if you look it up on the common ions list, you'll find carbonate with a 2 negative charge. So you need a subscript 2 to show there are 2 hydrogens so that we have a neutrally charged compound. However, having done this, bells and whistles should be going off in your head. Because this is the carbonic acid that automatically decomposes. So we can't leave that like that. We've got to change this into H2O and CO2. Because it has to be. It always does. That you have to know that. You have to memorize that. Like when you get up in the morning, you know to turn on the lights. Like when you go out of your room, you're going to put on your clothes first. Like when you're coming to school, you're going to get in your car. You just have to know it. Okay? Now, NH4 is ammonium. It has a 1+ charge. Chlorine has a 1 negative charge in a compound like this. In an ionic compound, it's going to have 1 negative charge. So I only need one of these and one of these. Chloride compounds are mostly aqueous. Ammonium compounds are always aqueous. This is aqueous. Okay, water, in the absence of any significant amount of heat, water is going to be a liquid. Okay, CO2, always a gas for us. Okay, all right, now we need to balance the equation. Now I'm going to shortcut this just for time. This is already balanced. You have to produce an atom inventory to show me. Okay, you can't skip it, but for time I'm going to skip it. Okay, are you with me? All right, let's write a complete ionic equation then. All right, this is an acid. I know it's an acid because it has hydrogen in the front. Okay, it's aqueous. If it's an aqueous acid, we split it up to write a complete ionic equation. So we've got H+, which is aqueous, and we've got Cl-, which is aqueous. Okay? This is aqueous, and it's an ionic compound. I know it's an ionic compound because it has a polyatomic ion here, and a polyatomic ion here, and if it has a polyatomic ion, it's an ionic compound. An ionic aqueous compound is split up in a complete ionic equation. So we have 2 ammoniums. This subscript 2 outside the parentheses means I have 2 ammoniums. 2 ammoniums. And it's aqueous because the compound is aqueous. And we've got 1 carbonate. And if you look on the common ions list, you'll see carbonate has a 2 negative charge. It's aqueous because the compound is aqueous. Okay? Now then, over on the other side, water. It's not ionic. It's not acidic. It's a liquid. There's no way, no how this is going to split up. All right, we got CO2. It's not ionic. It's not acidic. It's not aqueous. No way, no how is it split up. Okay? This is an ionic compound. It contains a polyatomic ion. It's aqueous. It's going to split. All right. Actually, you know what? I didn't balance that. I need a 2 right here to balance this, and a 2 here. So let me do that. All right, 2 here and 2 here will balance the equation. Now, having done that, then I need to change the number of hydrogen ions here. This is 2. Chloride ions, 2. Over here on the other side, I need 2 ammoniums and 2 chlorides. Okay? Now, this is a complete ionic equation. What do you do to write a net ionic equation? All right, I hear a lot of people saying all different things, but you're all saying essentially the same thing. We've got to get rid of the spectator ions, the bench warmers, okay? So hydrogen, no hydrogen over here, we keep that. Okay? And we're going to keep the water over here because there's not any of that on the left. Okay. Chlorine, I've got 2 chloride ions here and 2 here. Bench warmers, we lose it. Okay. Ammonium, I've got 2 here and 2 here, we lose those. The carbonate ion, we're going to keep that. It's not the same on the other side. And over here, there's CO2, and there's no CO2 on the left. CO2 and CO3 are not the same thing. There's a charge on this one, no charge on this one. This is aqueous, that's gas. They're not the same at all.